ME204, Rigid Body Kinetics using Non-Conservative Work. We've already talked about all the parts that go into the equation for energy for a rigid body. For kinetic energy, when it's translating, we have 1/2 the mass times the velocity squared. If the object is rotating, we have 1/2 the mass moment of inertia times the angular velocity squared. For potential energy, due to gravity, mass times the gravity times the height of the object. For springs, 1/2 the spring constant times the stretched or compressed length of the spring squared. We've also talked about work when we're dealing with translational work. Work is the product of a force, applied force, for a known distance. And we use the letter W for work. If we have a constant force, then our work is a force times a change in position. If we have a changing force, then it's the integral of the force times the change in distance. So what happens when we have rotational work? Well, again, work is the product of an applied force for a known distance. And when we had a constant force, we said that the work was a force times a change in position. What if we have a constant moment? Well, we still have work, but now instead of a force, we have a moment. And instead of a change in position, we have a change in angle. Notice that a moment is a force times a radius arm from a point of rotation. If we look at what the equation is for an arc length, S equals r theta, and we look at our equation here, where F times r times delta theta is equal to our work, if we remove the parentheses, we get force times the radius times a change in angle. But radius times the angle is an arc length, so we get a force times a change in position. The only difference is the change in position, instead of being linear, is an arc length. If we have a changing moment, then as with a force, our work is equal to the integral of the moment d theta. Now that we have our work and our energy for rotational objects, let's put everything together. We have our financial account balance equation again, where we have an initial balance, we add deposits, we take away withdrawals to give us a final balance. The same is true of our energy. Our initial energy plus or minus our non-conservative work gives us the final energy. We have kinetic energy plus potential energy plus or minus our non-conservative work equals our final kinetic energy plus our final potential energy. Writing out the full equation, we add on our 1/2 mass moment of inertia times angular velocity squared to both sides of the equation, and we also add in our plus or minus our moment times our change in angle. Anytime that we have an outside force or an outside moment acting on the system, we have non-conservative work that's part of our equation. Here's an example. If I have a 4-foot rod with a mass of 0.311 slugs and it's connected to 2 blocks that are confined to the smooth paths that are shown, vertical and horizontal paths, the block at A starts at rest when the rod is vertical, and then we apply a 2-pound force at A. Let's find what the angular velocity is of the rod when the angle theta equals 30 degrees. Also, let's see if we can figure out how fast block B is falling at that instant. We're going to neglect the mass of the blocks in this problem. We start by writing out our energy equation. We'll go ahead and write the whole thing, and then we can cross out what we don't need for the problem. Well, first of all, we can note right away that there are no springs in this problem. So we can eliminate the spring portion of the potential energy of the problem. The rod starts from rest, so there's no rotation initially, and there's no translation of the center of mass initially. There are no outside moments being applied, so we can eliminate that portion of the outside work. However, there is a force that's applied. We also have an initial height of the rod, and when the angle is 30 degrees, the rod will be rotating, its center of mass will be translating, and it will have an elevation. So here's our final equation. mgh1 plus or minus force times the distance equals 1/2 I omega squared final plus 1/2 mass times velocity squared final plus mgh final. Now we can go ahead and start plugging in the things that we know. Our initial condition for our rod is vertical. It's a 4-foot rod, and so the center of mass is located 2 feet from the bottom of the rod. In the final condition, the rod is at an angle of 30 degrees. Doing a little bit of trigonometry, we can figure out that the x component of that rod is 3.46 feet and the y component is 2 feet. Knowing that the y component is 2 feet, the elevation of the center of mass of that rod is located at 1 foot from the bottom. Plugging in our known values, our mass is 0.311, gravity is 32.2 feet per second squared, and the height initially is 2 feet, plus or minus the force. We've got an applied force of 2 pounds. That force is being pulled over this full distance of 3.46 feet, so we place that into our equation here. We also notice that that force is adding work to the system, or adding energy to the system. So even though we have a plus or minus sign, we're going to add that work to the system. Equals 1/2 our mass moment of inertia for a rod. For a rod, it's 1/12 ml squared. So here's our mass moment of inertia in our energy equation. 1/12, the mass, 0.311, and the length, 4 squared, times the angular velocity of the rod squared, plus 1/2 our mass, 0.311, times the final velocity of the center of mass squared, plus our mgh, which is our mass, 0.311, times gravity, 32.2 feet per second squared, and our final height of the center of mass, as we said earlier, is 1 foot. So we can place 1 foot in our equation here. Notice that we have one equation, but two unknowns. We have an angular velocity and a translational velocity. The relationship between velocity and angular velocity is v equals omega times r, where r is the radius from our center of mass to a point of rotation. But where is our point of rotation for this rod? In order to find this, we have to find the instant center. If we draw our velocities onto the ends of the rod and draw lines perpendicular to those velocities, then we can find the instant center. The radius to our center of mass is a straight line from the instant center to the center of mass of the rod. Now we just have to calculate what that radius is. We already know that the height is 2 feet from the bottom of the rod to the instant center, because we calculated that on this side over here. 4 sine of 30 equals 2 feet. And we know that the total rod's length is 4 feet, so the distance from the bottom to the center of mass is also 2 feet. Now we have two lengths and an angle. This interior angle here will be 60 degrees. So knowing two lengths and an interior angle, we can use the law of cosines to solve for our radius. So our radius is equal to the square root of 2 feet squared plus 2 feet squared minus 2 times 2 feet times 2 feet times the cosine of 60. That gives us 2 feet. So with a radius of 2 feet, we can put that into our v equals omega r equation up here, and we have a relationship between the velocity of the center of mass and our angular velocity of the rod. Once we have that, we can substitute that into our equation. Notice that we've replaced the velocity from this equation with omega squared r squared in this equation. Now we have one equation and one unknown, and we can solve for our angular velocity, which is equal to 4.52 radians per second. But what is the velocity of point B, or the top part of our rod at this point? In order to find that, we'll use our angular velocity and multiply it by the radius from the instant center to that point. That distance is 3.46 feet, as we calculated earlier. So the velocity at B is equal to our omega, 4.52, times our distance, which is 3.46 feet, to give us 15.6 feet per second. Our next topic is linear impulse of particles.